Hello, I'm Dr. Gilmet, and today we're going to do hypothesis testing for proportions, and I want to do this z-test in Excel. Alright, so I'm going to organize all the steps and do these calculations in Excel, and what I want you to know is I'm really focused on the mechanics today. The philosophy and understanding the process of a hypothesis test I've covered in some other videos. So what I really want to do is just sort of arrange the steps and do the calculations and show you how to do it in Excel because it's such a useful tool. So the first step is going to be write the hypotheses. The second step will be check the assumptions. Then we're going to do the calculations, and then I'm going to show you how to write a conclusion from that calculation, right? So here's the example we're going to walk through. From earlier polling, the CW believes that 34.8% of viewers watch Flash in their television lineup. On March 28, 2016, a crossover episode of Flash with Supergirl aired on CBS, reaching a different audience. The CW conducts a new random survey of 350 viewers and finds that 137 viewers watch Flash. Does this provide strong evidence that viewers increasingly prefer the Flash television show? And if you know me, if you've watched the channel for any length of time, you know I love my CW Arrowverse shows, so that's why I picked this particular one. So now we do want to write the hypotheses. Now, without going into great detail, the 34.8% of viewers is a dead giveaway that this is the population proportion with the trait watch Flash. So the 34.8% we're going to go over, and this is my population proportion. I'm not hitting tab, right? So my population proportion is going to be equal to the 0.348 in the problem, right? So that is the population proportion, is that 0.348. And then of course we're trying to figure out whether it's larger. Now my sample size is the 350 people that were in the sample, random sample of 350 people, and it finds that 137 viewers watch Flash, right? So the actual that watch Flash is 137. Okay, so this is what I got from the hypothesis and kind of reading through the problem the first time. Now what I need to do is check my assumptions. Is it random, right? Well, it does say random in the problem, so check, that one's fine. Is it independent? Is one sample going to be independent of another sample? Is one sample going to influence another one? Probably not. So if one sample is not influencing another one, that means yes, it is independent. 10% of the population. Now, I actually do this a little bit different. So this is my population check for the sample size. And so what we're going to do here is that I find super helpful is to multiply by 10. So because we're going to do a calculation in Excel, you always want to hit equal before you do the calculation. And so we're going to do 10 times the sample size. 10 times the sample size. And what we're asking ourselves is it reasonable? Is it reasonable to assume there are more than this viewers, more than 3,500 viewers? If that's reasonable, then this is mid-met. And I think it's reasonable to assume that more than 3,500 people watch TV, right? I mean, that seems pretty reasonable. Okay. The other thing that we're looking at, so if this is reasonable, then this is a yes. And then our sample size success failure condition, right? So for sample size, we check two things. We check the success condition and we check the failure condition. So for the success condition, basically we're taking the sample size times the population proportion, and we want to see if that's greater than 10. Now, some books will pick a different number. For the book that I have been using in my classes, it's 10. N times 1 minus P having to be greater than 10. That's the failure condition. And again, I go through this in detail, but basically if P is successes, right, then 1 minus P gives you what's left out of 100%, and then that would be the failure condition. So, I didn't want to quite go that far. So what do we have? Equal sign. The equal sign tells us we're getting ready to calculate. Sample size is n times P is my population proportion. That is greater than 10. And then here equals sample size, 350, times 1 minus my population proportion. That's greater than 10. So both of these are greater than 10. So my success failure condition is met, right? Oops. Sorry, guys. Okay, so now we're ready for step 3, the calculations. So now for the calculation, we need to find P hat. So here we go down, and now this is our sample proportion, right? For our sample proportion, again, equals our actual people who watch the flash divided by our sample size. All right, so actual people with the trait out of the sample size gives us 0.391. So that's our sample size. The next thing that we need after our sample size is our standard deviation for our sampling distribution, right? And so that's going to be the square root of P times 1 minus P divided by N, or the proportion successful times the proportion failure divided by N inside the square root. So our standard deviation is going to be equal to, for the square root, you do SQRT, and the open parenthesis sign will put that function in. And then we need the population proportion. Remember, you've got a lot of P's and P hats going around. So P is the 0.345. So if this is P, this is the 0.345, right? So 0.348, sorry, times 1 minus 0.348 divided by the sample size. And we close that up. So if you look, P times 1 minus P divided by N, all inside the square root. P times 1 minus P divided by N, all inside the square root. And you get 2.546, right? Now, after the sample size, now you're ready for your z-score. What's your z value for this particular thing? And so P hat minus P, so again, P hat, that's what we did up here. That's the actual successes. So my z-score, or my test statistic, is going to be equal to, right? Now you do need parentheses here because you got a subtraction in a numerator, right? So because of the subtraction of here, this needs to be in parentheses. So you're going to have your sample proportion minus your population proportion, and I'm going to close that up and then divide it by my standard deviation here. Okay, so remember the standard deviation right there, that's where it goes. And I hit enter, and I've got 1.7. So now my p-value, that's going to be equal to, now this is kind of a different function. What we're using here is the normal distribution. We're using the normal distribution because it's a set of proportions, and the central limit theorem tells us that this is what we're supposed to use, right? Now, you start typing norm, okay? In fact, let me start over. You start the equal sign. As you start to type normal distribution, normal.dist pops up, and it returns the normal distribution for a specified mean and standard deviation. It returns the probability of the area under the normal distribution for a specified mean and standard deviation. And so you can either double click on it or you can hit tab. I typically hit tab. The X is actually your z-score. the mean is 0 because we're using the z-score and it's a standard normal distribution, and then the standard deviation is 1, and then the cumulative is always true. Now the true is highlighted, and so you can either double click on it or you can type true or you can hit tab, any one of those. And what you get is this 0.95557, right? And so this is from the left. Okay, so you want to pay attention to this particular number right here and the fact that it's from the left. All right, this is from the left, and this would be for a alternative hypothesis that is less than. Okay, that's what you're going to have here for this. And the picture for it is here, right? Less than is to the left, and that's the 0.95599 blah, 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 right? So how do you fix that? Well, basically what you have to do is it's a percentage. It's basically 95%. So you want the other side, you do 1 minus the p-value, right? And that tells you from the right, oh geez, this caps lock thing is killing me, from the right, and that's for an alternative that is greater than, which is what we have. We have an alternative hypothesis that is greater than, right? And so this is actually the number that we want to use. This one right here is the star of the show. And again, if we go back to this calculator over here, instead of having the less than over here, what we would do is if we do greater than, you can see it's to the right, and shading to the right gives you the 0.0440. All right, so you can see that on that particular calculator. So you've got that going on for you there. So you would use this one if the alternative hypothesis is less than. You use this one if the alternative hypothesis is greater than. Because our alternative hypothesis is greater than, that's why I'm using this number over here, right? And so now we're ready for our conclusion. And so the conclusion is, because it's less than 0.05, because our p-value is less than 0.05, the idea is that we reject. And so what are we rejecting? We reject that the proportion of viewers watching Flash is 0.348, right? Because that was our alternative hypothesis here, the 0.348. And I'm just basically copying and pasting the proportion of viewers who watch The Flash, the proportion of, because why? We have evidence that the proportion of viewers who watch The Flash is greater than 0.348, right? Like, this is our, this is our idea right here, that this is the conclusion, right? It is highly improbable at random that we would get this sample, so we reject that it hasn't changed because we have evidence that it has. In simple terms, this would be the proportion has increased. We're fairly certain the proportion has increased. That's the true conclusion right there. All right. So that is the end of the video. I hope that helped you. And if it does, that makes me happy. See you next time on the channel.